think we have another speaker, local speaker, Renan Batalha. Sorry, I don't pronounce your last name. He's talking about the spectral dynamics of access to wormholes. So,
Thank you very much. Good afternoon, everybody. My name is Renan. Today I'll talk about some results of this work published last year in collaboration with Andreu Massó and Gonzalo Olmo from University of Valencia and Luis Crispino, my advisor. Well, so First, let me briefly talk about wormholes. Wormholes are these interesting objects defined by minimal two-sphere radius. The surface that has these radius is called throat and can connect separate regions of different or the same universe. Wormholes appeared in the literature a long time ago, and probably the Einstein-Rosen bridge is the famous one. Unfortunately, this solution is not traversable, but along the years, people try to construct solutions that you can cross the throat and go to the other side and make this transition. These solutions are known as traversable wormholes, and an example of these traversable wormholes is the ones produced via the thin shell formalism introduced by Matt Vister. Well, even though we don't have a clear description of the formation of wormholes, their phenomenology is so rich that it's interesting to study them, at least theoretically. And recently, very recently, it has been shown that wormholes are indeed ultra-compact objects because they have light rings. And in particular, if this wormhole is symmetric, the light ring is at the throat. Well, the light ring in a wormhole can be either stable or unstable, and depending on this structure, different phenomenology can appear. For example, if the wormhole at the throat is stable, particles and fields can be trapped there, and it leads to things like echoes in the ring Dow profile or additional peaks in the absorption spectra, and this is what I want to show you today, in particular in asymmetric configurations. So we considered an asymmetric wormhole constructed via the thin shell formalism in Palatini FO4. We chose this gravitational framework because it's possible to find either stable, either positive energy configurations and negative energy configurations. So we cut and paste two Heisenberg spacetimes and glued them together, creating a manifold geodesically complete. And we basically found these configurations here that are stable wormholes. And by stable here, I mean stable against radial perturbations at the throat. So Y in this parameter space denotes the charge to mass ratio in one side. Eta is the charge to charge ratio, and this X naught is the throat location. Well, as I said, it is an asymmetric configuration. So one Heisenberg spacetime has one charge and a value of charge and a value of mass, and the other has another value of charge and another value of mass. But here you are not seeing anything about the mass to mass ratio. It's because this value is constrained due to the continuity of the metric across the shell. Okay, so as we can see here, we have either negative energy density shells and positive energy density shells, and all of these configurations are stable. Okay, so we are interested in prove these geometries, and we choose the simplest wave-like probe, the scalar field, and we consider the dynamics of this field and these geometries. So due to the spherical symmetry, we have this equation, and where this V is the effective potential. It's important to point out that we don't have a delta type contribution in the effective potential. And it means that when we integrate and we cross the throat, basically the derivative of the field don't have jumps. Okay, so we also introduce this new coordinate, x star, in order to, with a single coordinate, describe the whole spacetime. Now, x star less than 0 is one side, equals 0 is the throat, and greater than 0 is the other side. Okay, so we consider these boundary conditions. We are considering here that the scalar wave is impinging from infinity. It interacts with the wormhole. Part of it is reflected back to infinity, and part of it is transmitted to the other side. And in particular, we want to investigate the scale absorption given by this expression, the scale absorption cross-section, and it is related with the transmission coefficients, this capital T. Okay, this quantity for black holes have two well-known limits. When in the low frequency regime, the total absorption cross-section goes to the event horizon area, and in the high frequency regime, this quantity oscillates around the classical absorption cross-section. However, for wormholes, these limits are not so clear, at least until now. Well, depending on the parameters, we can have different shapes of the effective potential. For example, we have these configurations with two smooth peaks connected by this valley, or we have a configuration with just one smooth peak. We can also have very weird configurations that are formed by these sharp peaks. And in the left, you have these configurations with just one sharp peak, and in the right, you have a configuration with one sharp peak, two smooth peaks connected by this valley. So as you can imagine, depending on these parameters and the shape of the effective potential, the behavior of the absorption is very different. Unfortunately, here I don't have time to show you all the results. You can find them in the paper, but I want to show you two results that I think summarize some of our main results. Okay, so here I want to emphasize the role of the symmetry. In the left, we have a symmetric configuration, and we have here the absorption cross-section of this symmetric configurations. As you can see, it is very different from a black hole absorption cross-section. And we have the presence of these additional peaks. These additional peaks are resonant peaks, and they are related with modes that are trapped around the wormhole. And when we break this symmetry and consider an asymmetric configuration, we notice that we still have the presence of the additional peaks, but now in the high frequency regime, it is more dilute, as you can see here. And this can be understood due to the difference between the heights of the peaks increases as we increase the value of the angular momentum L. Okay, and here, this last result, it's possible to find configurations of wormholes that mimic some properties of black holes. As you can see here, in the left, we have an asymmetric wormhole formed by this gluing game, considering a black hole in one side and a naked singularity in the other side, creating this geodesically complete spacetime. But the black hole side is basically the same as this one in the bottle. And basically, when we compute the absorption cross-section of these two configurations, we have this profile. And as you can see, in the high frequency regime, the behavior is the same, and it's basically the same. Of course, in the low frequency regime, it's not the same, since we don't have an event horizon. So in this low frequency regime, we don't go to the event horizon area. So these were some of my results. So thank you very much.
question, but I'm not sure if it is naive or not. I thought that these wormholes are unstable, and I think this is a work by Darío Núñez et al. Maybe Darío but I thought that this
Yeah, they're stable.
they are stable or unstable.
Stable. Stable.
All right.
Yeah, basically, if I can say some words about it. Yeah, so imagine that you are gluing this to space-times and you use a shell to do it. And you have this shell has a radius. So you perturb this radius and you can increase or decrease this radius. And you see what happens with this radius when you do this small perturbation. Basically, what you find is a harmonic oscillator equation. And basically, you see that this is stable when we perturb and basically return to this equilibrium point.
All right.